So this sigma y, or this sigma y, will tell you when the plastic deformation will start. بالتالي, you cannot initiate the plastic deformation if you are applying sigma less than sigma y. ممتاز. But if you remember, we say that we can correlate between what we see from outside changes in the dimension with what's happening inside the material. So in the elastic region, we say what's happening is we are elongating the bond between the atoms. And in the plastic region, what's happening, we said, the dislocations start to slip inside the material. And we said the definition of plastic deformation is the large movement, or the dislocation will initiate when you have a large movement of dislocations, right? Okay. Now, they want to dig a little bit deeper, and we want to say, how can we correlate between sigma y and the needed shear stress in order to let the dislocation slip? Because if you remember in the previous lecture, we said in order for the dislocation to slip, we need to apply shear stress, right? But I did not say that. I said, if in order for the dislocation to move or to slip, we need to apply high enough shear stress. So what we will learn today, we will learn about how we can correlate between whatever you're applying from outside and the shear stress that might be resolved as a consequence of the applied stress. And then we'll say, what is the high enough that will allow the dislocation to move? Okay? So in the previous lecture, we talked about slip system, right? We talked about slip system. And we say that the slip system is a combination of slip plane and slip direction, right? Slip plane and slip direction. This is why we have a table here that is showing to you, for each crystal structure, for FCC, BCC, HCP, what are the possible planes and direction, and their combination with the result what's called slip systems. And the slip system is the combination of a slip plane and slip direction. The slip plane is the plane that will result in a minimum distortion of atom, because the dislocation will move from point A to point B. The dislocation will move. The material will prefer that this movement from this point to this point would result in minimum distortion. To do so, the preferred slip planes will be the plane where the atoms are close to each other. This is why in a previous chapter, we talked about planar density and linear density. So for each crystal structure, the slip plane will be the plane where the atoms are closer to each other. So for FCC, it will be the family of 1, 1, 1. And for BCC, so 1, 1, 1 is a closed packed plane for FCC. For BCC and HCC, there will be no closed packed plane for BCC. So BCC, there is no closed packed plane, but there are planes where the atoms are close to each other compared to other planes within the BCC. Okay? So also this direction, 1, -1, 0, is the direction where the atoms are closer to each other. It has highest linear density compared to other family of directions. Now, if you look at, for example, 1, 1, 1 plane, if you look at 1, 1, 1 plane, you will see that for this plane, for this plane, there are 3 possible directions. So on this plane, the dislocation will slip to a certain direction, could be AD, it's possible. So this dislocation line will slip on this plane. Let me draw a dislocation line. So a dislocation line will slip on this plane to this direction. Or also, so before that, the combination of this direction and this plane, it's called slip system. And the combination of this plane and this direction is called another slip system. And the combination of this plane and this direction, DF direction, it's another slip system. So the combination of each slip plane and slip system is called, slip plane and slip direction is called slip system. Now, if you want to calculate how many unique slip systems, okay, you will find the total number of unique will be 12. Why unique? Because there are other slip systems that are equivalent to each other. Right? So the unique one will be 12 for FCC and BCC. You have 12, 12, 24. 3, 3, 6 for HCP. You notice that for BCC and HCP, you have more than one family of planes, right? But in your hand, remember that some of those planes or family of planes will not be active until you heat the material up to a certain temperature. So in room temperature, not all these planes will be active. Now, if you compare HCP with the rest, with the FCC and BCC, you will find there are less number of slip systems. What does that mean? That means there is less number of possible paths or ways for the dislocation to slip inside the material. So if this is a dislocation moving inside the material, and then this dislocation faced a certain obstacle, then what's going to happen? The dislocation, it might go to other paths and other planes and other direction in order to continue slipping. If there are more possible planes, the dislocation can move easier. If the dislocation can move easier, then you can do more plastic deformation. If you can do more plastic deformation, that means the material is ductile. Because the definition of ductile is the degree of plastic deformation. And plastic deformation requires movement of dislocation. So that means if you have more slip systems, the material will become more ductile compared to the other crystal structure where it has less number of possible slip systems. Great. Now what we will do, or before that, let me just delete this. The amount of the slip unit that we showed, we talked about last time, is equals to the Berger's vector. So Berger's vector, we talked about it in the previous chapters, and we can correlate the Berger's vector, okay? The Berger's vector, which is its magnitude, it's equal to the unit slip distance. Or for metallic material, we can say it's the interatomic spacing in this direction. Okay? So that means the dislocation will move with a certain distance, right? And that will result in a step at the end of the material. If the dislocations was able to make it from one point to another to the surface of the material, if you remember last time we talked about what's called unit step slip, is unit slip unit or distance or step, unit slip step, that equals to the interatomic separation between two atoms. So we can correlate between B, Burgers vector, for each crystal structure with the edge length of that crystal structure and the direction of the slipping. Great. Now the point or the question that we have, how are we gonna have a shear stress, okay, inside the material if we are only applying tensile stress? Imagine you got this cylinder and you're applying uniaxial stress, okay? Whether it's tensile or compressive. Now that stress, okay, will be decomposed into other components if the plane inside the material is not perpendicular to that plane. What do I mean by this? We know inside a single crystalline material, we have different planes of atoms, right? We have different planes of atoms with different orientation. So what if you are applying a uniaxial stress? That stress, although it is normal to the surface, this is normal to the surface, this one will not be normal to this plane anymore, right? So then what we need to do, we need to decompose this stress into two types of stress. The first one is parallel, which representing the shear stress into the slip direction, and a normal to the surface. So that means whatever you're applying from outside is the resultant of these two components. Or in other words, whatever you're applying from outside will be decomposed into two types of forces. One is parallel, the other one is perpendicular. That means even if you are applying pure tensile stress from outside to the material, that pure stress, tensile stress, will be translated into shear stress to planes, and the magnitude of that shear stress will depend on the angle, the orientation of that shear stress. The magnitude of the angle of that plane, okay? So here you're applying uniaxial load, and then this is the slip direction, which is parallel surface, and this is the normal to the slip plane, okay? And we need now to consider the angles that are correlating the axis of the applied stress F and the normal to the surface, and we call this phi. And the angle between our load, the axis of the applied load, and the slip direction, this angle we call it lambda. And then we can come up with this equation that is correlating the resolved shear stress on a certain plane inside the material with the applied stress from outside. And cosine phi, cosine lambda. So whatever stress you're applying from outside for a single crystalline material, so whatever I said right now, it's only applicable to a single crystalline material. We will talk later about if we have polycrystalline material. So for a single crystalline material, the applied stress from outside will be translated into resolved shear stress, and the value of this will depend on the applied stress and also the orientation of that plane. Good. Now, remember, I said earlier, the dislocation, as the plastic deformation will occur if we have large movement of dislocation. In order to move dislocation, we need shear stress. But I did not say shear stress, I said high enough shear stress. Now today, I would like to replace high enough with another word that we're gonna use from today and onward. That word is called critical resolved shear stress. So if the resolved shear stress reach to a certain value, it's called critical resolved shear stress. Then what's going to happen? Then the dislocation will move inside the material. So critical resolved shear stress, it's needed in order to activate that slip system, in order to let the dislocation slip on that plane. What does it mean if I am able to activate a certain slip system? That means I am able to move the dislocations on that plane. What does it mean if I move dislocation? It implies that if the dislocation moved on that plane, that means I am initiating the plastic deformation. But also how I can see this from outside if I look at the stress strain curve? Well, if I know the critical resolved shear stress, then I can predict what is the yield strength of the material. And the yield strength will equal to the critical resolved shear stress over the cosine phi cosine lambda. And this will happen if this is at maximum. Great. Then, by using this equation, I am able to correlate between the critical resolved shear stress and the yield strength of the material. So the critical resolved shear stress is a property of a material. At a certain temperature, it's a property of a material. Good. Now let's try to see what's going to happen if you apply uniaxial load, and that load resulted in shear stress. Okay, just a shear stress. Nothing going to happen. Dislocation will not move. But if you apply the old description was old enough. The new description is if you apply critical resolved shear stress, then the dislocation start to slip on certain planes. Those planes are the ones that have a favorable orientation. So the critical resolved shear stress will reach to those systems first. So what's going to happen? The dislocation will be moved on those planes. So will be moved until they reach the surface of the crystalline material, and then, or single crystalline material. And from outside, you will see something like a step from outside. So if you take a single crystalline material, apply uniaxial load, and that load resulted in or approach to critical resolved shear stress, then that's going to result, you're going to see steps on the surface of the membrane, surface of the specimen. That step is the result of movement of dislocations on that membrane. Great. Let's dig deeper. Let's take a real example and let's try to solve it. Let's try to apply whatever we learned so far into a problem. Okay, so one of the typical questions that is related to this is, consider a single crystalline material. It has BCC structure. And it's oriented such that the tensile stress is applied in a certain direction. So he told you what is the direction of the applied load. He told you it's tensile, so you know that from outside, the material will be exposed to uniaxial load, right? And he told the direction of that load, which is 0, 1, 0. The question is, compute the resolved shear stress, because today we'll learn that some of the planes, although this is a tensile stress, that tensile stress will be translated into shear stress. The question here, can you compute the resolved shear stress on a certain plane, 110, and that has slip direction -1 direction? Good? And he told you what is the tensile stress that he's applying from outside. So then the things are very easy, because what we're gonna do, we're gonna apply the equation. The the resolved shear stress will equals to sigma times cosine, right? Cosine what and what? Cosine phi and lambda. What is phi? What is lambda? Well, if this is the plane, okay, and this is normal to the plane, and this is the slip direction, this is the normal, okay, this is the direction of the applied stress, right? Now he told you this one is 0, 1, 0, and the slip direction is -1, 1, 1, -1, 1, 1. And the normal to the plane on a cubic system will have the same indices as the plane. And that will be, if this plane is 110, then this will be 110. Okay? Now the question, he wants you to compute the resolved shear stress. From the equation here, we got this. He told you it's 52 megapascal. And now we need to find phi and lambda. Okay? To find angle between two directions in the material, okay, I want you to look at this. Just give it a while. You just give it a second. Look at it. Look at this, and try by using a pen and paper. Okay, try to use this equation to find the angle between the two vectors. Okay, to find the angle between the two vectors. So what you will do, you'll say -1. So this is lambda, and this is phi, right? To find lambda, what we're gonna do, we're gonna say -1 times 0 plus 1 times 1, right? And you do the rest, okay? Between each two vectors. That will allow you to calculate the angle. Similarly, between this and this, you can calculate the angle. We'll give you 3 minutes, okay? Try to calculate the angle, the alpha and, sorry, the lambda and phi, okay? I'll give you 3 minutes, try to solve this. And if you're done, don't interrupt the rest of the student. Just يعني, if you have the answer, just leave it with you. I'm going to take the answer later. Okay, so can I get any answer? What do you think? You think it was easy to calculate the angle for lambda and phi? What's difficult?
Doctor, how we know how we know, like, do we need to choose 0, 1, 0 in the middle, or to choose this for lambda or this for pi?
So lambda, okay, good question. So lambda, this is whatever you are applying, okay? And this is the normal to the surface, and this is the slip direction. Okay, so this angle between your applied load and the slip direction is called lambda, and this one is called phi. Okay, now this one is given in the question, is 0, 1, 0 direction. Okay, and this one also is given, it's -1, 1, right, direction. And this one was not given, but because this is a plane, so the normal to the plane will be the direction with the same indices. So what is the plane indices? It is 1, 1, 0, right? So the plane is 1, 1, 0. So then the normal to that plane will be 1, 1, 0. Now all what I need to do right now is to find the angles. I need to find lambda by considering these two vectors, or these two directions, and I need to find theta by considering these two directions.
Doctor, why is not the normal to the plane is -1, -1, 0?
No, the normal is the one that has the same indices.
Okay.
The normal will be the one that has the same indices, right? Especially in a cubic system. Okay, good. So so here this question, if you want to plot it, it will be the direction of the applied stress 0, 1, 0. So this is the direction of the applied stress. This is the plane 1, 1, 0. This is slip direction -1, 1. Okay, and now we can correlate between their angles, and you can find the angles between them, and that will allow you to do what? To find phi by considering the angle between the applied stress and the normal to the surface, because this one is called phi. Okay, so it turned out to be 45. If you consider the parallel to the surface with a slip direction with the applied load, that will give you lambda. So then here you need to consider the direction, the slip direction -1, 1, 0, the one in the green color, and the applied load direction 0, 1, 0, right? If you plug these numbers here in this equation, it will allow you to calculate the angle between these two, directions. Now, if I have the angles, I mean, now I can identify the orientation of that plane, okay? And then what I'm gonna do, I'm gonna plug it here in this equation, right? The 52 megapascal was given in the question. So the resolved shear stress will be 21.3. So if you are applying 52 megapascal from outside, that will result in 21.5 megapascal for that specific plane. Let's go to the second part. So the second part is saying, if slip occurs, because the previous shear stress, the resolved shear stress was 21 point something, it's the resolved shear stress. It does not mean that dislocation will move as a result of that applied shear stress. The dislocation will slip if the resolved shear stress reach to a certain value. We call it the critical resolved shear stress. Now the question here is, if slip if slip occurs on the 110 plane in this direction, and the critical resolved shear stress is 30 megapascal. Okay, so he told you what's the critical resolved shear stress. Can you calculate the needed stress in order to initiate yielding? The answer is yes, because we know there is an equation that's correlating between the critical resolved shear stress and the yield strength. Now, if you go to the next page, okay, we're going to use this equation where we have the critical resolved shear stress over the, the angles, cosine of the angles, that will give you the yield strength. So if you applied 52 megapascal from outside, that will result in nothing. You will be in the elastic region. Why? Because that is not enough to let the dislocations slip on the planes, on slip planes. So it will not enough to activate the slip systems. If you apply from outside 73.4 megapascal, this stress, it's enough to activate some slip systems, and those slip systems will be activated because the needed critical resolved shear stress already been achieved, which is 30 megapascal. So the beauty of these two equations, okay, it's correlating these, the sigma y with the resolved shear stress, or the external applied stress with the resolved shear stress on the membrane, on the surface of the specimen. Now, in next lecture, we'll be talking about what's going to happen if we have polycrystalline material. Okay, what will be different than single crystalline material. So I will stop here, and I will see if you have any